Hello, mic test. Hello? Ako na ba yung mic? Oh, hello there. What's up, madlang people? Mga future biostatisticians. It's your boy, the one and only Sir Patrick of the Department of Biology. So I hope by now you have already read our syllabus and also the 2 supplemental video links that I tethered in our DLE course site. So I'm here today because we're about to start our first lecture for Bio 101 Biostatistics. So, shall we?
Wow, statistics. Do you guys really know what you're going into? That's just, wow, math. Really? It's a freaking fudge fest. Whew. Some of us really fear math. I know that. Well, back then when I was in my elementary school, I got really nervous just reciting the multiplication table. That basic, really. But I got scared. And that's okay, I think. Because then after you've done it and pass it, you'll feel a certain sense of pride to yourself. But to tell you frankly, what I'm going to try to solve and what we're going to do is we're going to make statistics edible for a biologist. Kind of like a book for dummies. A book for dummies thing. It'll be much more digestible and much easier, I guess. Because the problem with science is how we scientists handle our data, how we present them, how it scares the people, and make them dizzy. Our data should not only satisfy us, but should also be intuitive enough for the masses, especially on how we present them. Kind of like the idea of science for the people, right? So that's what we're going to do. The first question that comes to mind is, what is statistics anyway, right? Look at this cup. It says, statistics, the only science wherein 2 recognized experts using exactly the same set of data may come to a completely opposite conclusion. Because yes, sometimes that's how funny statistic is. So, but for real, what is statistics? Before, it is usually used by the state, by the government for data gathering. That's why it came from the Latin word statista, meaning statesman or politician. Because the government used statistics back then to monitor their people for demographic information, census data, for military recruitment, and also, more importantly, for tax collection. That's how the government works. And that's how the government is funded. FYI. But the German word statistic was the original purpose of it, is for the data to be used by the government for its administering body. And now, statistic is actually the analysis and interpretation of data with the view toward objective evaluation of the reliability of the conclusion based on the data. It's the practice or science of collecting and analyzing numerical data in large quantities, especially for the purpose of inferring proportion of a whole from those representative samples. Also, in here, we usually uses notations, like for example, sum of x or mean of x, or the average of x. Because if you don't, just imagine. No. Please imagine how difficult would that be. For example, instead of saying sum of cross products or sum of squares, we will say multiply every number in the first column by its partner in the second column and then add these products together. Now subtract from this sum the total number of the first column, multiply by the total numbers in the second column, but first divide this product by the total totals by the number of pairs of numbers now squared the answer. Divide this by the divisor obtained as follows. For each column, the number separately square, and then add the number and subtract from the square total of the column after dividing the square by the number of numbers, then add the results from two columns together. Instead of saying that, you could just say the sum of cross product squared over the sum of square of x for x plus the sum square for y. That's how easy. Or you can just write it in this way. You can get the answer. No, that's how seriously important using notations are in statistics. Okay? Okay, moving on. Statistics. Descriptive versus inferential statistic. So as you can see here, descriptive statistic provides a way to organize, summarize, and describe the data, while inferential or inductive statistic provides a way to make conclusions, generalization, predictions, or estimation based on the data from the samples. Okay? So descriptive statistic usually does not allow us to make conclusion from our hypothesis, but inferential one helps us objectively select which hypothesis offers the best fit explanation. So for descriptive, we have measure of central tendency, measure of dispersion, and variability. And for inferential statistic, we have comparison between two populations, between two or more experimental treatments. So that's the difference between them. Okay. So usually in statistics, we have variables or any characters, numbers, or quantities that can be measured or counted. In these variables, we have two kinds. We have quantitative and qualitative. The quantitative usually is in the form of numeric, and the qualitative are non-numeric, of course. So furthermore, our numeric quantitative variables have discrete or can either be discrete or in continuous form. Okay? Usually, our variables, from those variables, we can create data or any possible values or measurement that these variables can assume. From this data set, we can extract information. So that's how it works in statistics. Okay. Now, let's compare these two, okay? We have the first one, it says, the microplastic in the water column at two sites were measured, and the results show that one site had a higher concentration of microplastic particle than the other. Well, the next one says, microplastic in the water column at the two sites were measured, and the result shows that site A had a significantly higher microplastic concentration, and it gives us the value, particles per liter, than site B, and it also has the value. Plus, he also gave us the p-value of the statistical analysis that he performed. Now, if you see this in the field, no? Would you take the word of the first one? You're just going to trust him because he says that one site had a higher concentration of microplastic than the other without giving us a hard figure? No, that's the thing. If you gave them, if past scientists gave people a hard figure to look at, we're much more reliable, so to speak. Okay? So that's the thing with the statistics. It makes our interpretation and our data much more reliable. We have a wall to lean in during defense. What do you know about populations? In statistics, population is usually all the items that are being studied. It is the entire collection of measurement from which a person would wish to draw conclusions. There are, of course, large populations. For example, fruit flies in Baguio City, Benguet pines, trees in the Philippines, tadpoles in a lake. That's a very large population. And there's also a small population. For example, Bio 101 class of academic year 2017 to 2018 all cats that became roadkill along Governor Park Road from June to December 2016. And of course, there's also the imaginary or hypothetical population, like how many children you and your crush would have. It's entirely hypothetical, wishful thinking, right? Or like a man who is capable of sustaining a platonic relationship with an attractive female coworker. They are entirely hypothetical. Or for the case, the one that is in here in the PowerPoint, this species, this fish species, Posilia reticulata, is actually it's a freshwater species, no? So you won't find it in high level of salinity. So that's imaginary or hypothetical populations. And most likely, we will create a lot of that because of online mode of learning. Moving on. Populations. So there are large populations. Usually large population is hard, no, to study. It is best we set limitations to that as compared to a small population, because we can easily get all the measurements from a small population size. Now, what we will do if we are studying a large population? It is best that we set limitations with the limit this large population. Like for example, we set spatial or temporal or other delimiters to our population to avoid making generalizations with small sets of measurements. So we tend to delimit them. Like for the example, the first one, we delimit them by using space only the cats that died in Governor Park Road, not the entire national road system of the Philippines. And we also delimit it from June to December 2016, not the entire decade or year. Okay? That's how we delimit large population, because it is really hard to make conclusions for a large population if you don't delimit them. And it's really hard or difficult to get data too. That's the problem. Okay. So the other thing is, particularly in your thesis, we wouldn't recommend you to study the entire class of drugs with antibiotic properties. We just might let you study some classes like those that can inhibit cell wall synthesis, like penicillin, the lins, like that. Okay? So usually, in statistics, we do sampling. We do samples. These samples are usually a subset of all the measurements in the population. It is usually small, no? Because when the population is too large, it's actually unideal for us or unfeasible, no? It's really difficult for us to measure all the subjects in that population because there are too many, too expensive, and it will take a very long time if we do that. That's why we do sampling. Random sampling, no? To measure the sample characteristic and at the end infer the population characteristics na lang, so that we don't do all the populations or we don't measure the entirety of the population. So yeah, we usually get a subset or a sample denoted by small letter n from the population that is different from the population denoted by the large letter N. So instead of getting a population parameter or a numerical characteristic of the population, we instead get a statistic of the sample, which is much easier to get because it is smaller in size than the population. But what we try to do here is we try to infer from that statistic, from that sample n, the parameter characteristic of the population. Try to predict or infer, rather, this population parameter without really measuring every population, every member of that large population. Okay? So what is statistics? It is often used synonymously with sample data. So like vital statistics, 23, 28, 45, looking like a cone, or 40, 24, 34. We also have, so that's vital statistics. We also have enrollment statistics, 85% of pupil passers, so on and so forth. Something like that. But for here, we define statistics as the summaries or collection of numbers that describe a sample. For example, tallest is 1.72 meters, average height of this data is 53 kilograms, the range in weight is 44 to 68 kilograms. Something like that. Okay? Now, we have discussed that there is this population parameters versus the sample statistics, which is entirely different from each other. But what we do in here in statistics is we answer the question of how closely do the properties or characteristics of the sample statistics, approximate those of the population parameter. How the sample statistics approximate the population parameters. That's what we do here. Because we don't want to get very tedious, no? We only involve the sample, we only measure the sample to infer the population parameters. So if you look at this, you have a very large population. You want to know about them, this very large population. So you randomly select a sample for you to work with, and then you measure them. You get their sample statistics, you get sample mean, and so on and so forth. And then you infer na lang the parameter denoted by mu, no? The population mean. Here we have X with the bar on top, that's the sample mean, that's a sample statistic. And here, for the case of population, we have a mu, the population mean, denoted by the Greek mu, okay? So we denote it like that. Remember that. For population, we use mu, population mean, and for sample mean, we use X with the bar on top. Okay, so how do we do it? We use random sampling, right? And then we infer na lang the parameter characteristic of the population. Okay, so take a look at this mean weight of male student. We have a sample mean and we have a population mean back here. So as you can see, n, this small n equals something, is actually the number or sample size. So n is equal to 2, that's 2 samples, no? 2, and n is equal to 3, that's 3, and so on and so forth. So look at this. Can you see a trend? As you increase the number of sample, or take a look at this for the mean shoe size of female student. Look at it. N is equal to 2, n is equal to 4, n is equal to 16, n is equal to 25. Can you see something? Compare it to the population mean, the real size. So as you can see here, okay, as we increase the sample size n, as we approaches it to the real population size n, large n, no? As we increase it, as we approach the number of sample size to the population size, the sample mean gets closer and closer or approaches the real value of the population mean. So the statistic gets closer to the parameter. The sample statistic, as the sample size increases, get closer and closer to the population parameter. So that's the trick here. If we increase the population size, the sample size of our study, we tend to get a closer and closer values to the real population parameters. So that's how we make conclusions on the basis of evidence, no? That's how we infer, no? We base it on reasoning. It's really a stepwise reasoning from the premises of logical consequences, no? So that's what we do. We infer the sample statistic to the population parameter. Okay. Now, moving on, for biostatistics, we will always have the one thing about biological data really is, it's really variable. It's really variable, no? There's a lot of variation in your data. So there's this one, for example, one characteristic, height, for example, and you will see a lot of variation in height, or leaf length, or chlorophyll A concentration, or plant litter, organic matter, and so on and so forth. In dealing with biological data, we always get so much variation. And what do we do now? It's really hard, no? If that's the problem, there's this variability in the data that is caused by, well, the first sources of variability in your data is your intrinsic variation, or the inherent property of the organism or the thing that you're measuring, or the inherent variability within the same organism. So this intrinsic variation is actually within the organism itself. There's variation. That's the first source of variability in your data, in most biological data too. And the second source of this variability in our data is experimental or measurement error. So we all know that our devices, or our measuring devices, our instrument, usually has some error values, or some of them usually fluctuates their reading. So that's the thing here. That's the two primary sources. We will not include the human error because that's not acceptable, no? In science. We tend to lose faith when there's human error in your data. So as you can see here, I will introduce you to this graph. More difficult to get conclusive results with high variable data. That's the problem with highly variable data. So as you can see here, he says, sorry, we just can't trust you. Because look at him. This is what we call, this line is what we call, that line on top is what we call an error bar. That's an error bar. So as you can see here, this one, all of them have a very short error bar compared to this one that you see in the middle. He has a very large error bar. It's like a range of measurements. So that's why it means his reading is really variable. That's why you can't trust his reading back here. Okay, that's the problem with this data, with this person. So how do we handle this variability? No? Because there's a problem with variability in our data. We can't trust our data if it's really variable. There's a lot of fluctuations. It can sometimes be a pain in the ass. So how do we handle it? The first one is we try to describe and measure the extent of variability. So we tend to look at them and we predict or measure which group is more consistent or which group is more viable. And for this case, letter A is the one that is more consistent. Because look at the measurements. It clustered to a certain point. Unlike letter B that there's a lot of variability. There's two lows and they are very distant from each other. So that's the first one. We describe and measure the extent of the variability in the data. The next one is we determine the probability of correctness of the conclusion we make out of the data. So yeah, oh my god, size na. So yeah, which group is statistically larger? Is it A or B? Because letter B is higher than A. Look at that, right? Is B greater than A? Or are they actually equal? How sure are you? What we do here is we look at the error bar, so to speak. Because the error bar will tell us the spread of the data. So look at this. Although the mean or the average for letter B is quite higher than A, when you look at the error bar, it's quite large. So the data here is not trusted, no? Not reliable enough for us to make conclusion. As compared to letter A, that it has a very sharp or very short error bar. It has a very small range compared to B. So that's what we do. We determine the probability of the correctness of the conclusions. That's why we do statistics, actually. For biological data, we have different scales of measurements. We have data on a ratio scale, in which there's a constant size interval between units, and the tip here is data on a ratio scale has a true 0 point. For example, for dentitions, egg numbers, gill slit, the number of digits of an animal, the number of spore that it produces, the branches, the trunk girth, the distance of seed dispersal, the height, and so on and so forth. This is our ratio scale. There is a true 0 point. Unlike for the case of our interval scale, it does not possess a true 0. For example, your temperature time day of a year compass point. The 0 here does not mean really 0. Nothingness. That does not mean nothingness here. The 0 in our interval scale, unlike for the case of our ratio scale. Okay, it's data on an ordinal scale. So from the name itself, ordinal scale, it gives us the sense of order, ranking. So for example, long, longer, longest, small, medium, large. Something like that. It gives us a relative differences rather than hard quantitative differences among our measurements, among our data. Although the thing here with ordinal scale is that it contains a wee bit less information than, for example, our ratio or interval scale data. So examples of ordinal scale data is relative size, relative growth rate, relative light intensity, dark, darker, darkest, something like that. So that's our ordinal scale. Okay? And the last one for types of data is our data on a nominal scale, in which we have a variable or attribute classified by some quality rather than biological measurement. It's qualitative in nature. For example, eye color, taxonomic affiliation, habitat type, things like that. Okay, that's nominal scale. Okay, we rely on quality. So for the ratio scale, there's an ordered data, there's a constant scale, and a true natural 0. For our interval, it's an ordered data also. It's a constant scale, but no true 0. For our ordinal data, it's also an ordered data. There's ranking here, but the differences are not much important. For the case of the nominal measurement, we have a categorical data. No ordering is necessary for nominal types of data. Okay? For our numerical data, we have also two types. We have a continuous numerical data and a discrete numerical data. A continuous numerical data are variables that could have any conceivable value within an observable range. So there is a possible value between the two values that you have measured. There's a possible value between them. Okay? Like for example, weight, height, growth rate, O2 saturation, and temperature. On the other hand, your discrete data, your variables, your measurements can only take certain values. Like for example, academic loads, the number of teeth, the number of leads, seeds, and legs. Okay? Here, you can only take certain values. You cannot have an academic unit that is 1.333333 or a teeth that is 5.999999797. Something like that. Okay? There is a distinct or certain values that your data can only take. Okay? Can only have. Unlike for the example of temperature, you have a temperature that is 1.5999979 degrees Celsius, something like that. Or 1.59, ganun. Okay? But take for example this, no? Discrete data does not necessarily take on values of consecutive integers. Okay? You might get confused here because sometimes we in insects, among insects in entomology, we describe the organism by the proportion of wings and legs. So we have 1/3 or 2/3. So we do that. But that is a discrete data too. It's not a continuous data. Okay? They can only take certain values. Okay? So yeah, that's it for today. Thank you for listening. And before we end, I just have a certain activity for you. So this is per group, of course, where you will try to read write-up of scientific experiment or studies that you like. No? Preferably, you can use Google Scholar for this. So per group, provide 5 journal abstracts that fall within your topic and paste those journal abstracts, screenshot in a document, Word document, and you can identify the type of data that was collected in that study. Okay? So this is worth 20 points, 2 per journal. So that's 5 journals. And 2 points for correct identification of the variables that they have measured. Okay? That's the activity. For example, there's an example here. You can choose plant tannins. You can list all the variables measured and what type of data are they. They'll check it. You can submit it in our VLE. And yep, that's it for today. Thank you for listening. Thank you for your time. And if you have comments and suggestions, leave it in the comment box below. And see you again next time. Peace out.